IQ mismatch. So we are going to measure how much mismatch is tolerable by your transmitter. So assume that you have a phase mismatch of delta theta. So the I channel will have a phase shift of plus or minus cos delta theta. Q channel will have phase shift of plus or minus 1 plus or minus sin delta theta, just like a direct conversion receiver. And if you include amplitude mismatch, I'm going to scale it by alpha 1 and alpha 2, and I'm going to add two terms, delta AC, delta theta. So delta AC is going to be the change in the gain amplitude, and delta theta is going to be the change in the phase shift of your LOs. Okay, alpha 1, alpha 2 will take plus or minus 1, and normalized value. Usually, you get 4 points of the constellation. So the 4 points of constellation are given here: beta 1, beta 2. The four coordinates. Okay, where you have the constellation. And if if assume delta AC and delta theta are going to be 0, then you can see the value. It is going to be plus 1, 1, plus 1, minus 1, minus 1, 1, minus 1, minus 1. So if you plot the constellation, you will have it here. You will have the four constellation here. Normala, if you don't have any gain and phase shift, but because of gain and phase shift, this will be shifted. So the constellation may look like this. It will be shifted like this. So which is going to change your message signal. So the IQ mismatch is going to have a direct impact on the constellation of your transmitter. So another approach to quantify IQ mismatch is using two-tone. So just we have seen this many examples. You have seen this two-tone. Two-tone is sending two signals to I and Q to examine the output spectrum. You test the signal with the two-tone. Two-tone means two frequency signal. But here we are going to use the same frequency, but two variation of signal. One I'm going to use cos, one I'm going to use sine. And the output voltage will have uh, cos omega nt cos omega ct minus sin omega nt. So I can combine it to be cos of a plus b into t. In the presence of the mismatch, you will have a different term. This simplification, I have assumed that the phase mismatch and gain mismatch is going to be 0. But in the presence of mismatch, you see how much big terms we are getting. We have everywhere, we'll have delta, theta, and epsilon coming in your expression in the presence of gain mismatch and phase mismatch. And we are going to, similar to image rejection ratio, we are going to see what is the ratio of the image and your signal. So P minus by P plus, it is going to be this expression. You see again, it depends on epsilon and delta theta. Epsilon is going to be the gain mismatch, and delta theta is going to be the phase mismatch. Okay, so this expression is similar to an image rejection ratio, and we want the sideband to be suppressed as much as possible. So unwanted sideband of the image should be suppressed as far as possible. So in practice, they say the roughly the minus 30 dB will ensure the cancellation of distortion. So minus 30 dB difference, if you have it in the power levels, they say it is good for cancelling all your distortions. So if you are going to some calibration is required, or some quantification of the IQ mismatch is required for employing the same in the transmitter. So what if we have an unwanted sideband, can we use that power? How can you use that? Yes, but it is difficult to measure the power in the presence of largest wanted subband. So you have sideband, and you have to understand which sideband is required and which sideband is not required. So if you don't want any sideband, and if you want to suppress that sideband, you have to think whether I can use that power usefully or not. But they say it can be done, but it's very difficult to estimate the power and use the sideband effectively.